So before I continue to the 3D Laplace equation, I want to comment a little bit on the 2D Cartesian coordinates again. So could you keep quiet? So we're starting now. So if you really look at the ODE here along the x direction and the y direction, the only difference between the two expressions is that here the one is a positive constant and the other is a negative constant, and that will result in one set of solution being exponential functions, another set of function being sine and cosine. And however, I want to keep you in mind that the exponentials and the sines and cosines are not that much different. So you can see that if you go to the complex plane, the exponential of ix is actually related to the cosine x and the sine x, and the exponential of minus ix is also related to cosine and sine. So it doesn't quite matter much which k square you put here, like whether you put a k square minus k square here or minus k square here. However, if you made the correct choice in the first place, that will help you a little bit by eliminating the unnecessary conditions. And sometimes if you stare at the boundary conditions, you might already know that which kind of solution you need to put. So here, take a look at the sine function and cosine functions. These are oscillatory functions, and they can be starting from 0 and ending to a 0. And however, if you look at these exponential functions, they must start from something. If you give a finite regime, it must start from something non-zero to something non-zero again. And the only possibility for it to go 0 is to have an open boundary condition, and the e of minus x will decay to 0. So if you have this kind of perspective, like insight, and in the first place when you are considering this problem, then here you will recognize that here the v along the y direction has 0 on top and 0 on bottom. So you can immediately write down the solution that along this y direction it must be a sine ky. And then now once you have the sine ky on the y direction, on the x direction it must be an exponential function. So it can be an exponential of increasing function or exponentially decreasing function. But again, here on the infinity, it's a decreasing function, right? So this means that on the x direction, it must be an exponentially decaying function. And now then this is the way that you can immediately write down the complete set of solutions possible by this simple inspection of these boundary conditions. And then here this again the kn should be n pi over a. So this n pi over a is determining the boundary condition along this y-axis, and this v of v naught y at this x equals 0 will determine this c naught. And so this is a quick way of solving this 2D Cartesian coordinate for the first problem. And now let's take a look at the second problem. So in the second problem again, on the y direction it must be a sine ky. And on the x direction it can be exponential kx or exponential minus kx. But since it's an odd function here, then the combination of exponential minus x and the combination and the exponential of x will give a sinh function. Now this is for when when the boundary condition here is of two different signs. Now imagine that if I flip this boundary condition to a plus sign, then this sinh function has to be modified to be a cosh function. And that's because the cosh function is an even function, and only the cosh is allowed. And now for this plus sign, then you can have immediately also write down the solution to be sine kny and cosh knx. And again, it's a sum of all possible cn, and this kn takes the value of n pi over a, where this n goes from 1 to 3. So this is the quick way of solving the problem in Cartesian coordinates. Now bear that in mind, we go to the 3D solutions. Okay, so the problem here is similar to our previous problems, except that it's in 3D. So it's here considering a dice. Let's make actually the length of the dice possibly A, B, and C. So they can be not equal. So on 4 of the faces, the V should be 0, and say that this on top V is 0. On bottom, V is 0. On the left, V is 0. On the right, V is also 0. But in the front, V is finite constant. And in the rear end, the V is also a constant. Now let's take our intuition from the 2D. Again, we can separate out the x, y, and z coordinate. So here the V we write the V as a function of b of x, b of y, and b of z. Now, if we apply the Laplace equation, this simply gives us applying on this now taking the same trick, that is we simply divide the entire function by the v, and so the first term becomes, and the second term is the third term. Again, similar to the 2D situation, we really separate out completely the Vx, Vy, and Vz. So the first term only contains expression of V of x, and the second term and the contain only v of y, and the last term contain only v of z. Now, keep in mind that in the here, let me see. I haven't defined the x, y, and z. Say that this is the x direction, and this is y, z. So along the y direction and along the z direction, the v boundary condition should always be 0. And you can imagine that the solution of this must be taking the form of sine functions. And then this means here, for the sine functions, the constant is a negative constant, so we can assign a negative L square, and this is a negative k squared, and this is positive m squared. And here, the m squared should be really a combination, the sum of k squared plus L squared, to keep the entire expression to be 0. Now this means that the v of x then can be expressed as exponential v of y should be sine function, v of z should be again a sine function. Now the general solution of this should be simply a product of Vx, Vy, and Vz. And also we have the linear combination rule. So here the Vx, y, z should be this. This should be now let's check the boundary condition again. So because along the y direction, the potential must be 0 at both sides, and so here the cosine function must vanish, and the same is for the along the z direction, the cosine function also need to be vanished. And here along the x direction, because let's see, because the v is taking a finite value, so it can be a and b, that is something that we need to determine. Here I set the origin such that the 0 is at one of the corners, so we can no longer apply the expressions that we have for the sine and the cosine, because here it's not a simple even function or odd function. And so but here again, along the y direction, the k must be also take some integer values of n pi over a, and this n can be 1, 2, 3. Sorry. And this L again is similar, that it takes n pi over let me see. So along the y-axis, it should be sorry, I haven't specified the ABC correctly. The AC is redundant here. Say along the x direction, the length is A, and along the y direction, the length should be, let's say it's B, and along the z direction, the length, let's say it's C. And now here this K should be the having a length of B, and the L should have a length of C. Let me see. So here we need to determine the expression for the boundary condition along the x direction, which is A and B that we need to determine. And now if the boundary condition is set at 0, let's plug in here. So A plus B times sine ky sine LZ should be V naught, and the V at A YZ should be A equal A exponential of MA plus B exponential minus M so I think for simplicity, let's choose the origin somewhere in the middle of the x-axis. So let's shift the origin, otherwise it might be messy. So instead of looking at the a and 0 and the a, let's set this as minus a over 2. Let's define this as v naught. So this operation is simply shifting our definition of the coordinate system from origin to an a over 2 0 0, and that simply redefines our axis. So it goes initially from over here to over there, and by doing this, I'm making the boundary condition to be symmetric, which is the v is really can be written as the even function here. The v naught is symmetrical, so here that helps us specify the boundary condition here. Otherwise, the boundary condition, if we look at these two boundary conditions, you are going to get very messy results of a and b, and by shifting the origin, our solution can be a bit simpler because that only permits a and b to be equal. So this is the even function, and it can be expressed as a cosh. So let's simplify the expression here. So it's a constant times the cosh m of times x, and the sine k times y sine k times z. And now the next is to apply the boundary conditions. Either one of this okay, because the two are equivalent to each other right now. And then if we apply this at a over 2, this should be L. And this should be a single constant v naught. So from this, this should be, here c should be a function of n and n prime. Because here you can see that this k is the k depends on the n here, and the L depends on n prime. So there is a summation of n and n prime, and here once k and L is determined, this m is also automatically given. So sorry, I missed the m here. Should be m times a over 2, and then to determine this CNN prime, we use the same old technique of determining the 1D sine series. So here you can see that this is actually extremely similar to this 1D sine series expression, except that in 1D we only have sine ky here and a single sum. And now we have sine ky on one direction and sine LZ on the other direction, and the single sum becomes a double sum. So this is actually a 2D Fourier series. And the way of determining the coefficient of the CNN prime is exactly the same. So we apply the exact same trick as before. So the thing we need to do is to integrate from 0 to b and dy, integrate 0 to c dz, and multiply sine k prime. Sorry, this index might be a little bit messy. Let's call this n prime as m, and sine l prime z. And if we apply this operation to both the left and to right, we will get eliminate the double sum on the left. So what's left is Cnn prime, and it's the cosh ma over 2, and only one term will left for the sum over n, which is I believe should be b over 2, and the sum of over the l prime will n prime will also give the coefficient of c over 2, and this should be equal to 0 to b integrate over dy, 0 over c integrate over dz, and sine k prime y sine l prime z, and v naught. And then this will give, if you move the right hand side to, if you move the cosh terms to the right, that gives you the expression of Cnn prime. So what this essentially does is actually to also find out the overlap of the original boundary condition with this 2D Fourier series. And this Cnn prime is simply the overlapping coefficient. And once you determine the Cnn prime using this trick, then the boundary condition is satisfied, and this expression is really the expression for this expression for the in this bulk system, and should be the final solution to our answer. So here, generalizing from 2D to 3D is simply to generalize the one-dimensional Fourier series to two-dimensional Fourier series, and all the tricks actually carry through. Let's clear up the notation first. So along the y direction, the k takes value of n pi over c, where n goes from 1 to 3 into all the positive integers, and L, let's say that it takes the value of p pi over c, where p is a positive integer from 1 to 3. And then let's see, here this c should be the function index of n and p, and here the sum should also go from n and p, where k is the index of n, l is the index of p, and m is the index of n and p. And likewise, on the bottom, we need to edit these two things. So sum of np and cnp. And let's be clear about this. So it's mnp a over 2, and k over n, and l of P. Now here, what we need to modify is N and P. So here is N prime and P prime. So C N prime P prime should be an integral divided by cos and depends on P and A over 2 and B over 2 C over 2. Now this can be written out as 16V naught N prime P prime I square over cos and N prime P prime A over 2. So now if we here N prime and P prime are simply dummy index, and we can plug in this CNP expression back into the expression over here, and that gives our final expression. Of course, this is for N prime and P prime odd, just like before. And then if we plug in this C and N prime into the expression over here, we get the final result, and that says Vxyz should be 16V naught over pi square, and the sum over N odd, sum over P odd, 1 over NP sine N pi y over b sine P pi z over c, and times cos function, or cos n prime p prime, so it's square root of p square pi square over c square plus n square pi square over b square, and c x over cos m, again is the same, A over 2. Okay, so next let's try to solve the Laplace equation in spherical coordinates, and However, we want to simplify our problem a little bit. So even though it's a spherical coordinate, we still want the system to have an azimuthal symmetry. This means we are considering a ball, and the potential here can be a function of r and theta. However, along this azimuthal angle, the potential should be the same. This means that the potential should have no dependence on phi, and this means again in our 3D Laplacian can be simplified into 2 dimensions. So this Laplace equation in spherical coordinates should be read so it's just entire Laplacian applying on V. However, because our system doesn't have any dependency on the phi, so the last term simply drops out, and we are only considering the first 2 terms, just like the what we did with the Cartesian coordinates. And now here we do the exact same thing. So we have the potential that we first separate this into 2 terms, one that depends on r and another depends on theta, and then we apply we divide the expression by the v of r and theta again, and what's left over is 1 over vr, and this first term, sorry, this should be this first term only contains VR, and also another term that only contains v theta. So again, these 2 terms can be separated. So the first term will equal to 1 constant, and the second term will equal to a negative constant. Now let's define the constant here to be L times L plus 1. And the second one is L should be L times L plus 1, take an additional minus sign. And I will explain why it will take this strange value later. But for now, let's say that the L plus 1 should be the value on the left, and the minus L plus 1 should be the value on the right. So if we solve the first expression, we can see that and if we actually expand what's on the left, it should be this is simply expanding the Laplace operator on the left, and here you can see I need to apply this partial r both on the r square, and that gives the first term over here, and I also need to apply this partial r to this partial r, so that gives this term over here. Sorry, this should be. Let me see. I think I might have made a mistake. Let's go back. So the Laplacian. So the first term of the Laplacian has 1 over r squared, and I think I dropped the sorry, I think I've been a little sloppy. So here, because here there is a r square on both terms, so really this r square can be dropped out, and so here there should be a r square over here, and you can check. So if that's the case, then the first one applying partial r on r squared gives twice of r, and let me be clear. So it's 2r, and then applying this partial on the right and skipping this r square, then that gives okay, so this is the radial equation, and now let's check that actually this one we use a simple polynomial to see if this solve the problem or not. So see, we can check the first term. It gives 2r times s r to the s minus 1, and the second term gives r squared and s times s minus 1, and gives r to the s minus 2, and this should equal to L times L plus 1 of r to the s. Now we see that all these terms share the power of r to the power of s, and on the left is twice s plus s times s minus 1. On the right is L times L plus 1. So we see that on the left, this one is also s times s plus 1, which means here s could actually be L, right? However, that's not the end of the story. So S can also be minus L plus 1. So if you check that when S equals minus L plus 1, what's on the left is minus L plus 1 times minus L plus minus L plus 1 plus 1, which gives you minus L plus 1 times minus L, which is back to L. So really there are two possible solutions to this second order ordinary differential equation. So on the r direction, the general solution should be reading like and here A, B are arbitrary numbers. And now let's take a look at the angular direction. So in the angular direction, and this is the ordinary differential equation we want to solve. And the solutions, it's not a simple problem to solve, but mathematicians actually already solved the problem for us. And the solutions here should be written as and the PL are simply Legendre polynomials. So for simplicity, I've written this out here. So the V theta here, this capital theta is our previously defined V theta, and the solutions are V theta equals Legendre polynomial PL, the function of cosine theta. So this PL of x is one of the definitions of PLX can be neatly expressed in this compact form, but this form, from this form you can evaluate what the PL should be. So here I list a few of this leading order PLs. So for P0, it's a constant 1. So this means that 1 is one of the solutions to this angular Laplace equation, and the second one is x. Here, this x should be replaced by cosine theta, and this means that really the solution should be cosine theta, and here the solution should be the second order solution is cosine theta squared minus 1 and divided by 2, and now, if we combine the solutions on the radials and also the angular part, we arrive at the final general expression. So on the radial part is r to the L plus 1 over r to the L plus 1. And on the angular part is the Legendre polynomial of cosine theta. So you might wonder that here on the radial part we have two kinds of solutions. One is r to the l, one is r to the minus l plus 1. And on the angular part, we only have one solution. That's quite different, right? So previously, when we are talking about the Cartesian coordinates, we have always have two sets of solutions. Uh, say that sine x or cosine x, or it could be exponential x or exponential minus x. They always come in pairs. That's because it's a second order ordinary differential equation. But here, there is only one solution. The reason is that actually there indeed permits a second set of solution, but the second set of solution is not physical, which means that if you take a look at this expression, this is also one solution for the angular equation. However, this equation will blow up at some theta values. So when theta equals pi, this is tangent pi over 2, and it goes to infinity. So this solution actually is eliminated because they are not physical to us. So we only need to consider this PL cosine theta. And this actually, in a way, helps us already determine what's the coefficient in the theta direction. And we don't need to worry about the coefficient on the theta direction anymore. And what we need to worry about is the value on the radial equation. And in the next lecture, I will discuss how to solve this spherical coordinates. And okay, so just to summarize, we talk about the separation variables. We've already gone through the 2D and 3D, and we will discuss the 3D spherical in the next lecture. But for the homework, we will also doing with the cylindrical coordinates.